Hello, this will be a demonstration of proposition 12 from book 4 of Euclid's Elements, which requires us to, about a given circle, circumscribe an equilateral and equiangular pentagon. In the previous proposition, we had inscribed a regular pentagon into a circle. Now we're doing the opposite, we're circumscribing it. Likewise, we are given a circle A, B, C, D. And our task at hand is to circumscribe an equilateral and equiangular pentagon about this given circle. We begin actually by dividing the circle into 5 equal arcs. And the way we do this is actually by inscribing a regular pentagon into the circle, right? Because the pentagon is equilateral, so all of its sides are equal, it cuts off equal arcs by virtue of proposition 28 of book 3, I believe. And so if we inscribe a regular pentagon into a circle, it's going to divide the circle into 5 equal arcs, which is what we're going to do. Give me just a moment to figure out exactly how I'm going to do this. Not like that. And then okay, we're going to call this A, B, C, D, E, like that. And all of these arcs, AB, BC, CD, DE, and EA are going to be equal to one another. Again, we do this by proposition 411. If we inscribe a regular pentagon into a circle, then it's going to divide the circle into 5 equal arcs. So that's what we have here. We have 5 equal arcs now. And at each of these points in which the circumference has been divided, so at the points A, B, C, D, and E, we're going to draw straight lines tangent to the circle. We do this by the porism of proposition 316. So we begin by drawing the straight line GH tangent to the circle at the point A, which will look something like that. Next, at the point B, we're going to draw the straight line HK tangent to the circle. This is going to be rough, I realize. Next, at the point C, we're going to draw the straight line HL tangent to the circle. HL? No, it should be KL. Anyway. So that's going to be HL. Next, at the point D, we're going to draw the straight line LM, tangent to the circle at the point D. Like that. And finally, at this point E, we're going to draw the straight line GM, tangent to the circle. All right, so we're going to have something that hopefully looks better than my drawing. We have G, H, jump over I and J to get K, L, M, like so. Next, we're going to take the center of the circle, A, B, C, D, E. We're going to call this center point F. Let's put F about there. I'm going to erase the inner workings of this, just to make the prop easier to look at. Since these lines are not relevant, the pentagon itself that you inscribe into the circle is simply not relevant. It's only relevant that you divide the circumference into 5 equal arcs. Okay, so we're going to take the point F, like so. And finally, we're going to join these straight lines FB, FK, FC, FL, and FD. We do that, obviously, by postulate 1. I have a feeling I say that we didn't find the center by proposition 3-1. We do. So we find the center, 3-1, and then we join the straight lines from F to B, K, C, L, and D by postulate 1. Okay, so knowing that the straight line KL is tangent to the circle ABCDE at the point C, we know that the angles at C are going to be right angles. This is proposition 318. And likewise, we can prove that the angle is at B, so FBD is a right angle, and so too is FDL. Again, because those straight lines are tangent to the circle at those points, so the straight line drawn from the center to the point of contact, those 2 straight lines are going to be perpendicular. Okay, so now given that we have these right angles, we have actually a right angle triangle right here, FKC is a right-angled triangle, which means that by proposition 147, we know that FK squared must equal FC squared plus CK squared. Right, so FK subtends the right angle, while FC and CK contain the right angle. So the square on FK is going to equal the square on FC plus the square on CK. And likewise, the angle here at B being right, we know that FK squared is also equal to FB squared and BK squared. So we have these two sums of squares that are equal to the same square, namely FK squared. So they're going to be equal to one another. So we can say that FC squared plus CK squared equals FB squared plus BK squared, right? Because both of those are equal to the same thing, FK squared. So by common notion 1, we know that they have to be equal to each other. Okay. Now, we know that FB and FC must be equal to each other. We know this because they are both radii of the same circle. So by using definition 115, the definition of a circle, we know that FB here must be equal to FC, which means that the squares on them will also be equal, right? If you square FB, it's going to be equal to the square on FC. You think about that like numbers, 2 equals 2, 4 equals 4. Very simple. Okay. So FB squared equals FC squared, which means that we can actually subtract them from both sides by using common notion 3, right? If equals be subtracted from equals, the remainders will be equal. So we can say that CK squared is equal to BK squared. And if CK squared be equal to BK squared, we know that the straight lines themselves, CK and KB, must also be equal to each other. This is another property of magnitudes. So CK is equal to KB. Now, we had already established that FB is equal to FC, right? Because they're both radii of the same circle. And we have just discovered that BK is equal to KC. And between these two triangles, FBK and FCK, they have a common side, FK. So between these two triangles, FBK and FCK, we have 3 sides equal to 3 sides, which means that by proposition 1-8, these two triangles, FBK and FCK, are equal in all respects. Most importantly, for our present purpose, is that BFK is equal to KFC. Right, so the angle BFK is equal to the angle KFC. And so too, the angle FKB is equal to the angle FKC. Okay, so these triangles are equal in all respects, so we can say by proposition 1-8 that they're equiangular. Okay, cool. Now we can prove in a similar way. Oh, sorry, one more. So these angles being equal to each other, we can add 1 to both sides, and by common notion 2, we know that what we'll get will be equal. So let's consider our first angle. So angle BFK is equal to the angle KFC, which means that the whole angle BFC, which is comprised of BFK and KFC, must equal double KFC, right? So if we add KFC to both the angle BFK and the angle KFC itself, we get the whole angle BFC and double the angle KFC. So the angle BFC will be equal to double the angle KFC. And likewise, we can prove that the angle BKC is equal to double the angle FKC. And this is all by common notion 2. Again, it looks a little bit fuzzy because we're dealing with doubles, but it's fundamentally the same thing. Okay. Now we can prove in a similar way that the angle CFD, so this angle right here, CFD, is equal to double the angle CFL, right? We can prove that these two triangles, FCL and FDL, are equal in all respects to each other, which means that their angles are going to be equal. So we can do, again, this process of adding some of their angles together to get some more equal angles. So we can prove in a similar way between steps 4 and 6 that the angle CFD is equal to double the angle CFL, and so too the angle DLC is equal to double the angle FLC. Now, taking a bit of a different perspective, We know that the arc here, BC, is equal to the arc CD. We know this because we made the points on the circumference A, B, C, D, and E such that the arcs between those 5 points are all equal to each other. And so, we can say that the arc BC is equal to the arc CD. And the arc BC being equal to the arc CD, we know that the angles which stand upon them must also be equal to each other. That is proposition 327. So we can say that the angle BFC, which stands upon BC, is equal to the angle CFD, which stands upon the arc CD. And these angles right here are doubles of other angles. So halves of equal things are going to be equal to each other. And the angle BFC is half of the angle BFC is the angle KFC, and half of the angle CFD is the angle CFL. So again, halves of equal things being equal to each other as well. That is a property of magnitudes. We know that the angle KFC, right here, KFC, must be equal to the angle CFL. Like that. Okay. Now the angle FCK is equal to the angle FCL. We know this because all the angles at C we had shown in step 3 are right angles. And by postulate 4, all right angles are equal to each other. So the angle FCK is equal to the angle FCL. And the angle KFC is equal to the angle CFL. That is what we had just proven, which means that between these two triangles, KFC and CFL, we have two angles equal to two angles, and the side adjoining the equal angles equal as well, which means that by proposition 126, these triangles KFC and CFL will be equal to each other in all respects. Most importantly, that the angle FKC be equal to the angle FLC. And that KC right here be equal to KC be equal to CL, like that, which means that if we add the straight line CL to both sides of this equation, combination 2 tells us that the holes will be equal, so the whole straight line KL will be equal to double the straight line KC. Now we can prove in a similar manner. I'm not going to do it here. That's a bit too many steps for my liking. We can prove in a similar manner that the straight line HK is equal to double the straight line BK, which means that the straight line HK is equal to the straight line KL. Again, we can just go through steps 8 through 9 just with different triangles. So instead observing, I'm going to try and figure out which triangles exactly he's talking about. Okay, so if we join the straight line. Cool. Okay, anyway, so we can prove in a similar manner. The point is that we can prove in a similar manner that the straight line HK is equal to double the straight line BK, which means, and so too the straight line HK is equal to the straight line KL. Now, again, going through all of these steps, 3 through 10, we can prove that HG is equal to GM is equal to ML is equal to LK is equal to KH. What this ultimately means is that our pentagon right here, GHKLM, is equilateral. Now next we have to prove that it's equiangular, but you can see I've run out of space on the board. So I'm gonna put a cut here and move on to the next part of this proposition. So now moving on to proving that this pentagon, GHKLM is not only equilateral to equiangular, we shall reiterate that because the angle FKC is equal to the angle FLC, this was proven in step 9, right? So this angle here, FKC, is equal to FLC, and we know that doubles of equals are equal to each other. That is a property of magnitudes. And it was shown that the angle HKL was proven double the angle FKC. And likewise, it was shown that the angle MLK is equal to double the angle FLC. And so these doubles, the angle HKL is equal to the angle KLM. Now we can prove in a similar manner that the angle KHG is equal to the angle HGM is equal to the angle GML is equal to the angle HKL is equal to the angle KLM. is a bunch of just common notion 1 to show that all of the angles within this pentagon GHKLM are equal to each other. And so this pentagon GHKLM is not only equilateral as was shown earlier, but it has now been shown to be equiangular. And it is clearly circumscribed about our given circle A, B, C, D, E, which means that we've actually finished that which we set out to do. About our given circle A, B, C, D, E, we have circumscribed a regular that is an equilateral and equiangular pentagon GHKLM, which means we are done with the proposition QEF. I have simply nothing to add to this proposition, so I will simply move on to 413.